So, as I mentioned in the previous part of the lecture, things can get quite complicated in terms of algebra manipulation if you have more complicated expressions here to find the inverse Laplace. It's very important to understand that in this class, again, in the interest of time, and to make things a little bit more straightforward, we're going to focus on not too complicated examples, but we still have to handle sometimes expressions like this when we don't have just linear terms. So if your denominator splits into linear terms, so if you can factor this into linear terms only, you end up with always a bunch of exponentials, because you could split the partial fraction into fractions like this. But in practice, you also have quite often expressions like this. There is an even more complicated quadratic that can happen here when you have an s to the power 1 that still can be irreducible. You'll have to complete the square for that one. I will avoid that type of expression in the exams at least. So we're going to focus just on this situation when you have an irreducible quadratic of this form. So you have to make sure first that it cannot be factored. Because notice, if I had, let's say, s squared minus 9, that will be reducible. You could split it into s minus 3, s plus 3. With plus a positive, that's not reducible, so therefore you're going to end up eventually with those sine and cosine when you take the inverse Laplace. But this is an example when you have to take your time to take the fractions separately and do the partial fraction decomposition, because it takes a little bit more time and effort to do that, because you have more constant to determine. So when you do the partial fraction decomposition, remember, corresponding to each linear term, you have a partial fraction in that form. Corresponding to this term, you have a linear term on the top, and s squared plus 9, the quadratic on the bottom. Again, there's far more generality than this. You have also sometimes multiplicity. We're not going to deal with that for now. Besides, by the way, Maple or other computer algebra systems actually can do the partial fraction decomposition for you. But if you have to do it by hand, you proceed just like in the previous example, except you're going to have to use, you have to determine 3 constants in the end. So if you write the common denominator on the right, then 1, which is on the left, should be equal to a times s squared plus 9, and then s plus 1 multiplied by bs plus c. So the numerator is like that, and that must be equal to 1. Just like before, you're going to have to you have to combine the powers by the terms by the powers of s. So let's expand those parentheses first. So if I expand this becomes bs squared plus cs plus bs and then plus c, and the terms with s squared combine into a plus b. There's no s squared on the left, that means this should be 0. The terms with s combine into b plus c. Again, it's 0 because there's no s on the left. And finally, the constant is 9a plus c, which is 1. So this can get actually as complicated as a system that needs to be solved by Gauss elimination, right? I mean, again, I'm going to avoid those situations when you end up with larger systems that require matrix, row reduction and other linear algebra techniques. In this case, you could exploit the fact that you can eliminate quickly b from the first 2 equations. So if I subtract the 2, I get a minus c equals 0, and I can combine it with the third equation, and then I have a 2 by 2 system. So if I add the 2, then we have 10a equals 1, which gives me a equals 1 over 10. And then we can quickly find the other terms from the first one. If a is 1 over 10, that immediately gives me b minus 1 over 10. What else? C, right? So from the second equation, minus 1 over 10 plus c That gives me c equals 1 over 10. All right, so that being said, then we can replace my original fraction with this combination. And remember what I told you before, you're going to break this down over here as well, because you're going to use two different formulas for that part, right, of the formula when you do the inverse Laplace. So a over s plus 1, that's 1 over 10, 1 over s plus 1, plus bs over s squared plus 1. Now b was minus 1 over 10, s over s squared plus 1, and then plus c, which is 1 over 10 again, 1 over s squared plus 9. It's very important to go slow on these examples. Make sure you do the computation yourselves and understand each step. Don't rush this at all. You will be able to do it faster once you get the hang of it. It's all mechanics here. I mean, just remember how you learned derivatives and integrals. It wasn't as fast in the beginning. Now I'm sure you can take the power rule quickly, right? If I ask you to differentiate t to the 3, let's say, you immediately say 3t squared. But remember, there was a time in calculus 1 when you took some time to actually process how you do that. Take the same time here, because it'll get better and faster, but not if you skip the practice that you need. So before you do the linearity property, notice these two match the table. 1 over s plus 1 matches the table. S over s squared plus 1 matches the table. This one doesn't, right? You need b on the top. B is equal to 3 in that formula. So that means I need 3 on the top. I need to produce it. Multiply and divide by 3 the entire fraction. So now I can use the linearity property. Let's just use it directly and use the formula. So 1 over 10 comes out. L inverse of this becomes e to the minus t. Minus 1 over 10, this goes into cosine of 3t. And this 1 over 30 comes out, and you're left with sine of 3t. And that's going to be your answer. All right, I might have to change this. The ink is drying out. So that is the example. Kind of like the most difficult example you will see. Not more difficult than that in an exam or in the homework. So for the last part of the lesson, I would like to actually point out, just to anticipate, that's actually part of the second lesson. You know, how do you actually solve differential equations with the Laplace transform. But we have actually time and room to just provide a quick example on how that comes to be. So in the notes, I provided a proof of this formula, but if you look at the table, there are two important formulas related to the Laplace transform of a derivative. That is the key formula that connects this whole game with solving differential equations. So if you look at the formula in the table, you will see that the Laplace of the derivative of y, so the Laplace of y prime of t, is equal to s big Y of s minus little y of 0. So remember the convention of notation, big Y is nothing but the Laplace of little y of t. So let's focus on this formula very briefly. I mean, not briefly, carefully, I mean, before we move on. And see why actually this connects basically the differential equation. Well, obviously it's connected because you have Laplace of y prime, but notice that the Laplace of y prime is in terms of the Laplace of y of t. So that means potentially you can change the problem from an integration problem when you have the derivative to an algebra problem when the unknown doesn't contain a derivative at all, but contains just a function that you may be able to find. So that is the beauty of the Laplace transform, because it moves you immediately from analysis, let's say, to algebra. to find little y of t, you don't do an integral. You're going to solve for the Laplace transform of the unknown. And then once you find this, you can take the inverse Laplace and find the answer. So again, in a nutshell, the beauty of the method is I don't have to do any integral to solve the ODE. All I have to do is to simply compute, by any means possible, the Laplace of the unknown, this big Y of S. So we're going to get back to this formula and the one specific to y double prime when we actually move on to how to solve differential equations by the Laplace transform. But I want to just use this formula very briefly in a very simple linear ODE that you may be able to actually solve by other means, right? So notice also that you need y of 0. That's another thing to keep in mind when you do this method. You're going to need to specify an initial condition. So for example, let's say I have to solve an initial value problem which states, let's say, y prime plus 2y equals 4, and y of 0, let's say, is equal to 1. So an initial value problem. And in fact, well, let's leave that. I was going to do it actually even easier than that, but let's keep it at that. So again, we're going to go over more details next lecture, but the main idea in solving a differential equation by Laplace transform is to start by taking the Laplace transform of both sides of the ODE. Okay, so you move the problem via Laplace transforms. Use linearity property, so this is L of little y prime plus 2 L of little y equals L of 4. Now use the formulas in the table. So the table states that this is S big Y of S. I'm not going to write Y of S because we understand that big Y is in terms of S, minus Y of 0, which is 1. Okay, so L of y prime, according to the formula, is S big Y minus Y of 0, which is 1. And then this is 2 L of little y, which is big Y. And again, from the formula, from the table, L of 4, move the 4 out. L of 1, it's 1 over S. So again, I want you to pause for a moment because this is worthwhile to appreciate it. We have a differential equation. We take the Laplace and we end up with an algebra problem, not a differential equation. It's just a matter of solving for big Y and hopefully getting back via inverse Laplace to little y. And that's the solution of the ODE. So from this point on, it's just manipulation, algebra manipulation, so you can collect the y terms together, factor y times s plus 2, move the 1 on the right hand side, and we can combine the denominators here. This is going to be s plus 4 over s, and then finally, I mean not finally because there's still more work to do, but big Y is going to be s plus 4 over s times s plus 2. Okay, so what do you do now? All you have to do is to go back to the original little y via the inverse Laplace transform. Some work to do still, right? I mean, we have to split this into partial fractions of this type. That means s plus 4, the numerator, is a times s plus 2 plus b times s. And if you group the terms, this becomes a plus b times s plus 2a. So I hope it's clear that a plus b should be 1, the coefficient of s, and the constant, which is 2a, should be 4. So that gives me a equals 2 and b equals 1 minus 2, which is minus 1. So the Laplace transform of the function that I need to find is a over s, that's 2 over s, and then minus 1 over s plus 2. Okay, we can take the inverse Laplace to find little y of t at this point. It's a very straightforward combination. So 2 over s goes back into 2, and then 1 over s plus 2 goes back into e to the minus 2t. So your solution is of the initial value problem is 2 minus e to the minus 2t. We can actually check y of 0. If I plug in 0 for t, 2 minus e to the 0 is 1, so it satisfies the initial condition. So let's not rush this moment before we move on with the second lecture of this chapter to see what actually entails the whole method. So first of all, the method solves immediately, directly, an initial value problem which is linear. It deals with both the general solution and the initial condition, right? You don't have a separate moment of finding the concept of integration. So the Laplace method deals with both. You start with an initial value problem and you are given the solution once you're done with the process. What does the process entail in general? You take the Laplace transform of all sides, you move the problem into an algebra equation in big Y of s. You solve for big Y of s, and then by any means possible, splitting it to linear into partial fractions if necessary, right? You're going to find the inverse Laplace of big Y, which gives you little y of t, and which of course is the solution. One final remark, because many of you may think about this. Now, what's the advantage of doing this via Laplace transform when this type of LDE, if you remember, you could do it very quickly via the two-step method, right? So you could take the homogeneous part of the equation and say, okay, the homogeneous part is c to the minus 2t, because remember, that's an exponential, ODE, c to the minus 2t. And then a particular solution, it's very easy to see that it's 2, because the particular solution is in form of a constant, right? 0 plus 2 times 2 equals 4. So you could do it quickly, in a couple of seconds, in fact, that the general solution is c to the minus 2t plus 2. And of course, you may have to take an extra step to find c from the initial condition, but it's no big deal. Just plug in 0 for t, and then c equals minus 1, and there you go. You get your solution via the two-step method in a much faster way than via Laplace transform. So the take-home message is that you're right, in fact. If you're thinking about that this is the easier way, you are right. The Laplace transform is not really invented to deal with problems like this. We do these problems just to learn the method, to practice, but where the method shines is when you have more complicated functions. Like, for example, if you have discontinuous functions on the right-hand side, or some more general types of inputs here, this is where the Laplace transform is useful, not for simple expressions like this. And also for standardization purposes, which you will see later when we study convolutions, which is another application of Laplace transform. So I think that's enough for today. It's really important to take your time. Don't move on to the second section on the chapter until you actually process this. We have some time to catch up. Do expect some time, more than a day, to spend on 8.3 on the third section of the chapter. So really allow 2 days, go slow, and don't move on until you really practice enough with these types of calculations, taking the Laplace transform or its inverse. That's the main focus in the beginning of the chapter. So I'll see you soon.